So now that we've talked about what an acid and base is and we've talked about pH, let's look at actual experiments involving acids and bases. And an experiment that involves an acid and base is what's called a titration. And a titration experiment is used to determine the pH or the molarity of a given acid or base. So what happens is sometimes we're given an unknown substance and we don't know, an unknown concentration of a substance. We know it's an acid or we know it's a base, but we don't know what its molarity is. So what we're going to do is we're going to use a known substance with a known concentration to compare it against. And we're going to conduct this experiment and produce a titration curve. So what I'm going to show you now is using the virtual chem lab, an actual experiment that involves an acid and a base titration. So you can kind of see what's going on before you go and do it in the lab. So this is what your titration experiment is going to look like. This device that is here, this long glass rod, is what is called a burette. Okay? A burette, it works like the graduated pipettes that we were using in the Beers Law lab, in which 0 is at the top and 50 is at the bottom. So you fill the liquid all the way up to the top, and you can see a little screen of the burette view here on the left-hand side. So you fill it all the way up to the top at 0, and then as you open up the valve on the bottom, the liquid will pour out, and depending on what the volume says, tells you how much you have added to the beaker that's on the bottom. Now typically when you do this, you're going to put the base in the burette and the acid in the beaker. I would say probably 3/4 of all experiments are conducted like that. Base in the burette, acid in the beaker. There's a couple of exceptions to that, but that's not really important at this level. In our beaker is going to go the substance we're studying, which in this case happens to be hydrochloric acid, the indicator. Now in this indicator we've decided to use bromocresol green. It doesn't matter what indicator you use. This one just happened to use that one. And this one changes yellow. It's a clear liquid. You can see it from the container itself. But it changes yellow in the presence of an acid. And then we've also got in here our pH meter. Okay, and so our pH meter is this long rod, and the pH meter that we're going to use looks very similar to it. It's black at the top, but ours happens to be blue. It's the only exception. And at the very bottom is a little glass ball, and inside that glass ball are 2 little wires. And the wires actually shoot electricity between them and measure the amount of H plus ions that are in solution. And so the more H plus ions there are, the more electricity that can jump between the 2 wires. And that reading is sent back to our pH meter. And our pH meter is going to be connected to the computer so that everything will graph right in front of you and be ready to go. So I've got my pH reading here. It's 0.91, so it's a very, very acidic solution, which makes sense. It's 0.3 molar. And this is my graph on the side. And the computer will, when you do this experiment, the computer will also graph it for you as you go. So, and of course, we've got our stirring solution going on at the same time. So we've got our stir bar going because we want to make sure that our acid and our base mix completely. Now, in the experiments you're going to conduct, you're actually going to do this by pH, not by volume. So in other words, you're going to add enough volume to change the pH by a certain amount. But in this example, I'm just going to show you what happens as you add base. So I'm going to begin to open my valve. So notice that when the valve is perpendicular to the burette, then it is closed. But the more parallel it becomes, the more the solution will pour out. Okay, so at this angle, you can see I've got a pretty steady rate of about 1 drop per second, a little bit faster than 1 drop per second. And you can see that my volume is dropping on the left-hand side, and the pH is beginning to rise slowly, which makes sense. I'm adding a base to an acid, and I can see that on the graph, and I'll make the graph the focus in a minute. Okay, and again, I don't really care about precision here, so I'm going to let it flow out a little bit, just so I can get a much better graph. Now, in your experiment, you've got to be much more exact than this, okay, because you want to make sure you record exact volumes and exact pHs. So notice that in the beginning of the experiment, the pH change is very, very slight, okay? That's because the solution is like 95% acid and 5% base. And as I add that base, it's being neutralized by that tremendous amount of acid that's present in the solution. The less acid there is, the more neutral the solution becomes. So you can see in the beginning it's very high concentration of the acid in the beaker, but slowly as the acid gets neutralized, the graph begins to rise a little bit faster and a little bit faster and a little bit faster. Turn off. There we go. Okay, Now you notice the graph is starting to make a pretty sharp rise. So I'm going to slow this down just a little bit. A little bit faster than that. There we go. So I'm going to get this steady rise. So it's going up, it's going up, it's going up, it's going up, and now it's making even more of a rise. And all of a sudden, you notice something very dramatic. Oh, there it is. Look at that gigantic jump that happened. Okay? What has happened here, and I'll talk about this more on a bigger graph in a second, is I have now passed the point where my solution is all acid, and now my solution has become all base. You'll also notice I have taken your attention away from it, so hopefully you'll rewind and go back, but you'll also notice that my solution has changed color. Okay, that's the purpose of the indicator. The indicator is going to change when that solution has shifted from one pH to another. Now, bromocresol green happens to change right around a pH of 7 or 8. So as I passed that 7-8 mark, all of a sudden my solution changed. Now, you notice that I've gone up, I've crested, and I'm starting to flatten out again because I am primarily sodium hydroxide at this point. And it doesn't really matter, so I'm going to turn off my burette, because this will just keep going and going and going until eventually I hit the pH of my sodium hydroxide, because now my solution is about 90% base and only about 10% acid. Very, very little acid that's still left in this solution. So let's back out of this experiment, and I'm going to show you a bigger graph of this, what's called a titration curve, and I'm going to diagram out some important parts of it so that you know where things are occurring. So now that you've seen the acid-base titration virtually, you're of course going to experiment with the lab. But what I want to do is I want to break down what's called the titration curve that was produced in this experiment. So again, this was your pH. This is the volume added. Now in this case, we added a base. So you would say volume of base added. Okay, but it doesn't really matter. It's always volume added, and it's always in milliliters. Okay, so this section here on the bottom is where we are all acid. Okay, I can tell this because the pH is very low. Okay, the pH is below 6, and it's basically flat. Okay, if my pH was high, then it would be a base, like this section up here. So these sections are where it's about 95% of that substance. So it's 95% acid, 95% base. Now we really don't care much about the stuff on either end of the titration. What we care about is the point that's right about here. Okay? This point here in the middle is what is called the equivalence point. Okay? The equivalence point is where the moles of your acid equal the moles of your base. Now that's not concentration. It's not where the molarity of acid equals the molarity of base. It means where the moles of the acid that I had in the beaker before the experiment are now equal to the amount of moles of base that I have added to the experiment. So they are exactly equal. Now, if you are dealing with a strong acid and a strong base, that point will occur at about a pH of 7. Sorry. pH of 7. There we go. Okay, so because they have completely neutralized themselves. The acid is gone, the base is gone, and I'm left with what we'll talk about later is a salt solution, a water and a salt of some sort. Okay? Now, how do I determine each of these numbers? Well, it's really easy, because when you do this experiment, the problem that you're going to have is you will have a big jump in a pH. Okay? So what you do is you take the volume of base before your biggest jump, and you subtract the volume of the base after. I'm sorry, you don't subtract. You find the volume of the base before the biggest pH jump. You find the volume of the base after the biggest pH jump. Okay? And you take the average. And that's equal to the volume added at the equivalence point. Okay? So in this particular experiment, let's say the volume at before was 21.5 milliliters, the volume after was 22.0 milliliters, so the average between the two would be 21.75 milliliters. Okay? So now that's not the moles, that's just the milliliters. Now that I know the milliliters, if I know the molarity, I take the volume times the molarity, and that will tell me the number of moles, and then I can work backwards to figure out my acid. So this is a nice, easy way to determine the molarity of the acid, because I always know how much acid I put into the beaker. So it might say, put 10 milliliters of the acid into the beaker. Oh, well, if I had 10 milliliters before, and I know there's this many moles, moles divided by milliliters is base. I'm sorry, moles divided by milliliters is molarity. So it becomes a lot easier to do. And that's what you're going to do in that titration, acid-base titration lab, is you're going to perform a titration, you're going to find your pH before, you're going to find your pH after, you're going to get this beautiful curve, and then you're going to figure out how many moles were added at the equivalence point, and it'll walk you through. Now, there's one other thing that I want you to take a look at on these curves, and that is your my brain just shut off. Your indicator, okay? You typically want your indicator change to occur immediately before or immediately after your equivalence point. Now, ideally, you want it to occur immediately before your equivalence point so that you know you haven't passed it. But some of them, sometimes we have no choice and we have to deal with something that occurs after. For example, and we'll talk about this in a minute, but phenolphthalein changes at about a pH of 8. Okay, so if you're dealing with a strong acid, strong base titration, that's a pretty good indicator to use, because strong acids and strong bases will have a pH, have an equivalence point at about 7. So as soon as you've passed that equivalence point, bam, your color will change. You know to stop, and you know that you're at the right point right there. Other ones like methyl orange or etc. will change right before, so that tells you you're getting close. So it all depends on what the purpose of the lab is to determine which indicator is best used. But usually you want your indicator to change somewhere in the range of your equivalence point. And we'll talk about other indicators in a later podcast. And that's an acid-base titration.